let us once again gather what we have up until now. Bruh. Bruh.
Bruh.
Good morning, fellow mathematicians. Welcome back to another video. My number Bartholomew Ligma. And this right here is actually the first video being recorded using Hagoromo Chalk. Or, I mean, I'm writing on the board using Hagoromo Chalk. So this means from this point onwards, no video can go wrong anymore. It's all the videos from here on out are bound to be fucking amazing, okay? So, I tell you what, this sum right here, this infinite series, okay, I came up with 3 different ways. One is my standard method, I would say, by doing a double integral thingy. One is the intuitive, I'm being a jet motherfucker boy method. Okay, I'm going to make a video on that too. But today we are going to deal with this infinite series right here in one of the coolest ways ever. I mean, it's just a collection of so many freaking cool analytic number theory things, and we are going to dive right in. It's going to be absolutely amazing. Seriously, watch this till the end to see the gift card giveaway, to get your riot points. No, at this point people just want some Fortnite points or whatever they are called. So at first I would like to factor out the 4 for reasons that will become apparent in a second, okay? Meaning we are going to end up with, oh, it's so smooth, it's so legendary, this bloody chalk. If we factor out the 4 right here, okay, we are going to get a 4 square down here, so let's bring this to the outside. It's going to be 1/16. Gotta blow a bit of the chalk dust away. But also we are going to get our infinite series from k being equal to 0 to infinity of 1 over. We are going to get rid of the 4 in front of the k. But if we factor out the 4, we also have to have a 1/4 right here, because if we multiply everything by 4, we want to get our 1 back, meaning plus 1/4 squared. And this thing right here is something we've actually talked about before. This thing is called the Hurwitz Zeta function, but evaluated at special values. This is nothing but this infinite summation, 1/16 times the Hurwitz Zeta function in normal case of s, comma, our set value that we would have right here. You can also define yourself the Leersch transcendent. Then we are going to get, this is nothing but Hurwitz Zeta of 2, this is the s, comma, 1/4. And we're done. Thank you guys for watching. This thing has a special value. You can look it up on Wikipedia. Now we are going to calculate it, because the special value we are going to get out of this is actually something pretty amazing. It's one of the not so many known values of a really special function we have talked about before. Now I would like you guys to remember how our Polygamma functions looked like. I've made a video on the Taylor series expansion of the Digamma function, and in this process we had to calculate an expression for our Polygamma function. Why is this important? Well, our Polygamma functions, if you remember correctly, I'm terribly sorry, being speech mentally disabled right here, our Polygamma functions are nothing but -1 to the s plus 1th power. Then we are going to get s factorial times the Hurwitz Zeta function, okay, that's supposed to be this thing up here, of, if I remember correctly, s plus 1, comma z. This is how our Polygamma functions looked like. Meaning, how can we get to our Hurwitz Zeta function of 2, 1/4? Well, why not plug in 1 for our s to get 2, and for z just 1/4. Meaning, if we take a look at this right here, we can actually just plug stuff in. Our Polygamma function of 1, the first Polygamma function is actually the Trigamma function. I have made a several video on that because there's no point in doing so. This thing is just called the Trigamma function, not the Digamma function. It's called the Trigamma function, comma, 1/4. Being equal to -1 squared is nothing but 1. 1 factorial is nothing but 1, okay? Meaning we are going to be left with our Hurwitz Zeta function of 2,1/4. Now, isn't that really cool? So you see, this infinite series right here is actually nothing but our Trigamma function evaluated at 1/4. And this right here, finding this fact out is extremely powerful, just because we know what our digamma function is, and we know that we can define our polygamma functions, and thus especially our trigamma function, as nothing but the derivatives of our digamma function. Meaning, if we know what the digamma function is, we can just differentiate it with respect to some variable, and then we are going to arrive at our trigamma function. Okay, so this is really cool. And for this purpose, I actually derived something different before. Okay, I want you guys to remember that we can express our digamma function. Okay, so the 0th order polygamma function of S, I'm going to put it like this. Don't confuse this S with this S right here. It's a different index. I'm just going to put S here because that's how I derived it before. Okay, our digamma function of S can actually be expressed as negative Euler-Mascheroni constant plus some integral from 0 to 1 of 1 minus x to the s minus 1th power over 1 minus x integrated with respect to x. Meaning, how can we get to our trigamma function or the polygamma functions in general? Well, we just have to repeatedly differentiate this thing with respect to s. Meaning, just doing one iteration, dds, of our digamma function is going to be nothing but our trigamma function of S or Z, whatever you wish. You can also plug a Z into here if this confuses you, this change of variable right here that we are going through at the moment. And well, this is pretty cool. Okay, so in this process we are also deriving something different. We are also deriving an integral representation for our trigamma function in this case. Okay, maybe I'm going to make a separate video on that also. So what happens if we differentiate this with respect to x, with respect to s? Meaning this thing right here, trigamma function of s, is actually nothing but dds of negative Euler-Mascheroni constant plus an integral from 0 to 1 of 1 minus x to the s minus 1th power over 1 minus x integrated with respect to x. If we differentiate that, well, our differential operator is linear, meaning we can differentiate at first the Euler-Mascheroni constant, it's just a constant, just like the name says, so this is going to vanish, and then we can differentiate this integral with respect to s. For this, we are going to make use of Feynman integration, you could say, the Leibniz rule for integrals. So you see another technique being used right here. Under certain conditions, if this thing converges right here and shit, we can actually interchange this limit and this limit, namely the integral, bring this to the inside, and since the upper and lower bounds are independent of s, we can make use of the special case of Leibniz rule, meaning we are going to bring this differential to the inside, but we are going to turn this into a partial derivative with respect to s, because this thing in itself is a multivariable function, it's f of x comma s. Okay, so we are going to be left with an integral from 0 to 1 of del s, 1 minus x to the s minus 1th power over 1 minus x integrated with respect to x. And this is really easy to differentiate. 1 over 1 minus x is just a constant, we can bring it to the front. Also, if we differentiate 1, it's going to be 0, so this in the process is going to vanish. Negative 1 is just a constant, we can bring it to the front. And x to the s minus 1th power, I'm going to put a side note here. X to the s minus 1th power is nothing but e to the s minus 1 times the natural log of x. Okay? We have used this fact extensively before. Meaning, if we differentiate this expression with respect to s, we are going to be left with natural log of x times, so the inner derivative of this thing, times our exponential function being preserved. But our exponential function is nothing but x to the s minus 1th power. Meaning, we are going to be left with an integral from 0 to 1. Okay, the Hagoromo is a little bit thick. I couldn't reach down here the lower part of our 0. Then we are going to be left with, okay, negative natural log of x times, okay, x to the s minus 1th power over 1 minus x integrated with respect to x. We can distribute the negative sign into here, turn around the signs, and then we can actually plug in the value of 1/4 into our s. Okay, meaning we are going to be left with Trigamma function of 1/4, 1/4, being nothing but an integral from 0 to 1 of something over x minus 1. Also, if we plug this into here, for reasons that will become apparent in a second, I'm just going to put the 1/4 here, okay? This is nothing but x to the 1/4 power times x to the negative 1. I'm going to put it like this, times the natural log of x, integrated with respect to x. Now we are left with an integral. So once again we have turned our summation into an integral. And don't forget, we also have to multiply this final result by 1/16. Okay, just imagine all of this being multiplied by 1/16. Now here comes the substitution in, which comes in pretty naturally. Okay, so what we want to do is we want to let some, I don't know, let's say tau, okay, tau, just because tau is pretty cool, be equal to x to the 1/4 power. That's why I put it separately, meaning d tau is nothing but, we are going to reduce this thing actually by a 1, meaning it's going to be just x to the negative 3/4. Also don't forget, we have to drag this to the front, this 1/4, and then times our differential dx. Cool thing is, x to the negative 3/2 is something that we already have. If we just take a look at this right here, x to the s minus 1, if we plug 1/4 in, that's 1/4 minus 1 is negative 3/4. So in the substitution process, we are going to get, okay, upper and lower bounds are going to stay how they are. If we plug 0 into here, it's going to be tau being equal to 0. And if we plug 1 into here, 1 to any power is just 1, you could say, okay, if we take a look at the principal branch, then dx times this chunk is nothing but, well, 4 times d tau. Okay, we can multiply both sides by 4, and then we are going to get this. So 4 times d tau. Then we are going to get natural log of x. But what is x? X is nothing but tau to the 4th power if we raise both sides to the 4th power. So natural log of tau to the 4th power over, and then tau to the 4th power once again minus 1. This reduced quite nicely actually. All that's really left to do is to bring the 4, this 4 to the front, and also we can use the natural log property to bring this 4 to the outside and also to the front, leaving us at the moment with this being 16 times integral from 0 to 1 of natural log of tau over tau to the 4th power minus 1 integrated with respect to tau. Okay, so what's the next plan? So you see the cool thing is this 1/16, and this 16 would cancel out if we go through the whole process, meaning our summation at the moment is just this thing right here. Now we want to evaluate this, and I want you guys to consider something. This down here is nothing but the difference of 2 squares. So this is nothing but tau squared, but squared once again, meaning we can decompose our denominator into tau squared minus 1 times tau squared plus 1. And what we want to do now, completely ignoring our numerator, we want to decompose, partial fraction decomposition, our 1 over this stuff into 2 new fractions. That's the next thing we are going to do. Then we are going to plug everything in and see what we are actually going to get. Okay, I hope you are still excited. Bruh! Just as a quick reminder how awesome this right here is. We have turned our summation into the Hurwitz Zeta function. We have discovered that our Hurwitz Zeta function is nothing but our Trigamma function. Okay, and also we have turned our digamma function into an integral representation for our trigamma function. And now, after doing a lot of work, we actually ended up with 2 integrals we have never seen before. We have kind of seen some of them before, just with other upper and lower bounds, but not how they are presented right here. And we are going to start with the first one. I'm going to call this thing I right here. And we're going to dive right in. So now for I. What can we actually do? There are different things you can now do. Okay, so the first thing I actually tried right here was to turn the natural log of tau into, well, the Taylor series expansion, but that ain't Gucci. I mean, you can kind of factorize this right here into t minus 1 times tau plus 1, not t tau, but it's going to cancel out kind of, but it's not going to be Gucci. One thing we can do better right here is at first factor out a -1 down here. Okay, so this thing is actually equal to negative integral from 0 to 1 of the natural log of tau over 1 minus tau squared. How does this help? Well, the cool thing is we are just going to turn this down here, so 1 over this chunk, into the geometric series. Okay, that's something we have done before extensively. So that's negative integral from 0 to 1 of, okay, now we are going to have the natural log of tau times the Taylor series of the geometric series, not the Taylor series of tau squared, you could say. So summation running from k being greater or equal to 0 of, well, in this case, tau squared to the kth power, being tau to the 2k, integrated with respect to tau. Now, on this interval from 0 to 1, our geometric series actually converges absolutely and uniformly, meaning we can interchange this summation and this integration, just interchanging the limits right here. Okay, let's bring this to the outside, leaving us with negative sum running from k being equal to 0 to infinity, an infinity boy, integral from 0 to 1 of natural log of tau times tau to the 2kth power, integrated with respect to tau. And this is where all the magic is actually going to happen. So we are going to partially integrate, that's the easiest thing we can actually do. We are going to differentiate the natural log of tau, because finding its antiderivative is not too elementary, you could say, and we are going to integrate our tau to the 2kth power. Meaning, if we take a look at this little table, di plus minus, one iteration is going to do the job. Differentiating the natural log is going to give us 1 over tau, and integrating, well, in this case tau to the 2kth power is going to leave us with 1 over 2k plus 1 times tau to the 2k plus 1th power. Okay, I hope you agree, right? So 1 over 2k plus 1 times tau to the 2k plus 1th power. Now we are going to multiply this together right here, and then we are going to take the integral of this whole thing and see what we are actually going to get. Meaning I is nothing but, now we are going to get negative this summation of, okay, I'm going to put a big parentheses around this. So we are going to have upper and lower bounds from 0 to 1. That's our table right here. At first we are going to get the natural log of tau times tau to the 2k plus 1th power over 2k plus 1 from 0 to 1. And then second part of integration leaves us with a negative sign. So negative integral from 0 to 1 of, I'm going to put this constant stuff in here, I don't have enough space left, it really doesn't matter. 1 over tau, and this tau to the 1st power is going to cancel out, just tau to the 2kth power over 2k plus 1 integrated with respect to tau. Okay, coolio. Now let us do some analysis on this first part right here, because it's going to completely vanish. So if we plug 1 into here, natural log of 1 is nothing but 0. Okay, all stuff is going to vanish. Now here comes the only problem. If you plug 0 into here, well, that's natural log of 0, that's going to negative infinity, times 0. So if we bring this down here, we are going to get a negative infinity over infinity situation. You're now going to see a little outtake of me doing L'Hopital. You can find this outtake on the second channel. Bruh. And if we now let tau approach 0, this is actually going to vanish, going to go to 0 in the limit. Now that we have talked about this, we know that this goes to 0 in the limit. That's cool on both upper and lower bounds. Also, this negative sign and this negative sign is actually going to cancel out. Okay, and what we are left with is this thing right here, and this is just the integration of a simple polynomial, leaving us with sum running from k being equal to 0 to infinity of if we integrate tau to the 2k power, we know what this is going to evaluate to 1 over 2k plus 1 times tau to the 2k plus 1 power. We also have this factor here again, so tau to the 2k plus 1 power over 2k plus 1 squared. And all of this from 0 to 1. If we plug 0 into here, that's just a simple polynomial starting from degree 1. Okay, this is going to vanish. It's going to be 0 all the time. If we plug 1 into here, 1 to any power is just simply 1, leaving us with something we have talked about before. Something pretty dope. So this is nothing but 1 over the reciprocal of all the odd numbers squared. I've made a video on that. I've made several videos on that actually. This right here is nothing but pi squared over 8. Isn't that pretty dope? Meaning, this first part is actually going to be pi squared over 8 times 1/2 pi squared over 16. Okay? All that's really left to do is to evaluate this thing right here. And I want you guys to notice something. This works out completely analogous. All that's really different is that we are going to get negative tau squared when doing the geometric series. Meaning we are going to be left with a negative 1 to the k power term right here. Okay, this is something that's going to happen, meaning in the end we're actually going to be left with an alternating series of this kind. And we have talked about this before. This is going to be once again an outtake because it works completely analogous. In a few seconds you are going to see what this is actually going to evaluate to. Like I said, outtake on the second channel, my boys and girls. That we are going to get the alternating starting on the first term in the normal case, which would result in g, our Catalan's constant, but we better bring this negative sign to the front because this thing right here is Catalan's constant, leaving us with negative g. Now that we have this out of the way, we actually can fill in all the gaps because we turned our infinite summation into this ridiculous thing right here. Okay, this has been a long journey. But what is this exactly? This is nothing but pi squared over 16. We have talked about this before. Pi squared over 8 times 1/2. Negative, and negative is going to become positive, plus g over 2 in this case. Catalan's constant over 2. And this is pretty ridiculous if you ask me. And this right here, like I said, is one of not so many values of the Trigamma function that we can actually evaluate, which has a closed form, you could say. And if we get rid of this 1/16, we actually get that our Trigamma function evaluated at 1/4 is nothing but pi squared plus 8 times g then. Isn't that pretty cool? I mean, it's it's so amazing in my opinion that we can actually calculate something like this, and this has real value in closed form. I thank you guys for watching. If you did enjoy this, Hagoromo boy, please like and subscribe and recommend channel if you like. Here once again, Hagoromo Shike, best Shike where is, made out of angel tears. If you want to support channel a bit more, buy those t-shirts I created, or support the channel on Patreon. Buy those stupid t-shirts I create, or yeah, I don't know, click on my Quora questions from time to time, and up until the next video, have a flammable day. Love you guys, appreciate ya. Ciao.